This video is going to cover classification theory. So we're going to need this to understand a method called discriminant analysis, which is a very old classification model. It goes back to Ronald Fisher, very famous statistician from the early part of the 20th century. But it's still a very important method. And this classification theory gets used in a wide variety of machine learning models. So you're going to see a lot of the same concepts when you study something like latent Dirichlet allocation in text mining, or Gaussian mixture models with segmentation approaches. So it's a very general approach, and it's worth knowing. Discriminant analysis, even though it's such an old method. So here's the problem. I'm going to suppose that there's K populations, big K populations, and we can label them 1 through K if we like. And I'm going to assume that there's some random variable big Y that indicates the group to which some observation or sampling unit belongs. Now, we're going to describe these K groups with a variety of distributions. So there's really three main distributions that we're going to be using. So one of them is called the prior distribution. So the prior distribution is I like to call this the unconditional probability of group membership. So unconditional means, if I don't have any extra information. So I draw a person at random from my population. The probability that that person is in group, Y is going to be given by the prior distribution. So let's call these probabilities pi sub Y. Now, these K groups are mutually exclusive and collectively exhaustive. So what that means is every person has to be part of one of these K groups. And therefore, the sum of these probabilities must be 1. Okay, so another way to say this is if I draw somebody, they have to be a member of one of the groups. They can't be a member, they cannot be a member of some group outside of my K groups. They have to be a member of one of these K groups. Now, in addition to this random variable Y, we're going to know some other things about my sampling units. And these are going to be called X's. So in general, we're going to have P of these attributes that we can measure. And so for each sampling unit, I have a vector, x1 through xp, giving their measurements. Now, the class-conditional distribution of x for a given group is going to be denoted by f sub y at x. So I think we need a simple example of this. So I'm going to go over to my document camera for a second. And let's consider an example where I have p equal to 1 x variable. And so maybe x is a person's credit score. So we're going to keep this extremely simple with only one x. And let's say that I have a population with two groups. So this is one group. So this is the credit score of this group. So that's the x. And then I have another group that is sitting somewhere over here. All right. So the red group is all has all defaulted on a loan, where the blue group is the group that did not default. So they paid you back. The red group did not pay you back. So what I'd like to kind of illustrate with this is Let's say that the defaulted group has y equal to 1, whereas the non-default group has y equal to 2. So using my notation, f2 at x is going to be this normal curve. So this would be a normal PDF, so probability density function with a certain mean, we'll just call that mu2, and a certain variance. So let's say the variance of this is sigma squared 2. Then this distribution is going to be f1 at x, where the mean of this is mu1, and let's say the variance of this is sigma squared 1. So using my my language from that slide, these two normal distributions are class-conditional distributions. So class-conditional. So the way to think about this is I've told you which class a group is in. So if I say this is the defaulted group, then the class-conditional distribution describes the distribution for that group. Alternatively, I could say this is the non-default group, and then, well, the class-conditional distribution for that group is the blue one. All right, what's the prior distribution in this case? So the prior would be this. What is the probability that I observe a person at large from the population who defaulted? So what that means is this is not default, and this is going to be pi 2, whereas the probability that I draw someone at random from the population who defaults is going to be pi 1. And so what we know is that pi 1 plus pi 2 is equal to 1. Therefore, we really only need one prior in this case. So it's extremely important to understand the meaning of these two distributions. So the prior, this is the prior here, is I just draw a person at random. What's the probability that they're in one of the groups? The class-conditional distribution is this normal curve depending on whether you defaulted or you did not default. All right, let's go back to my course packet for a second. In real life, we're going to observe a training set with n observations, and so we'll just denote those by x sub I. So x sub I is this vector. We may have more than one. In my little example with the credit score, we only had one x, but there might be many. And then we observe which group that person is in. So we have training cases. We know whether or not some sampling unit defaulted on the loan or didn't default on the loan. So our goal in classification theory is to develop some rule that allows us to classify observations conditional on x. Now, the way we're going to get to this is with something called the posterior distribution. So the posterior distribution is just the probability of group membership for a given x. So let's go view this on my figure over here. So why don't I take a different color? We'll just go with black. You probably can't tell the difference between blue and black here, but that's okay. We'll use a subscript. So let's say that I observe some person's credit score, and the credit score is this. Let's just call that x1. All right, so what the prior distribution would say is, how likely is it that someone with this credit score defaults versus doesn't default? So I think in this case, the probability that y is equal to 1, so in other words, default, given x1. Okay, so that's what this is saying. this would be pretty high. This would be large. So in fact, it would be close to 1. Because if the real distribution is this blue one over here, how likely is it that I am going to observe an x value way out in the tail? Well, not very likely. It's much more likely to have come from this red distribution. All right. Likewise, we would say the probability that y is equal to 2 given x1, so this is the non-defaulter. We'll just write that non-default, is going to be small. In fact, it's going to be pretty close to 0. So an observation here is much more likely to have come from the red distribution than from the blue distribution. Well, I'm going to go take a Sharpie now, and let's take a point, say here. So this is going to be x2. That doesn't show up great, but let's just consider x2. So what is the probability that y is equal to 1 given the value of x2? So if I come in and this is my credit score, what's the probability that I'm going to default on the loan? And so the answer is probably fairly high, but not as high as the blue distribution. So I'm slightly more likely to have come from this blue distribution than the red distribution, but there's a substantial probability that I came from that red distribution. So I'm just going to say maybe that's 0.4, whereas the probability that y is equal to 2 given x2, so this is the non-default, might be 0.6. So this is saying I'm slightly more likely to be in this blue distribution than the red distribution, but you better worry a bit because there's a substantial probability I'm going to go away. All right, one more, x, if you will. Let's go take the pink one over here. This is pink, and this is x3. And so in the case of x3, the probability that I default given x3 is going to be close to 0. So how likely is it that I've come from this red distribution if my x is way out there? It's not very likely. Whereas the probability that's a given sign there, y is equal to 2. So what's the probability I'm in this non-default case given x3? Well, that's going to be close to 1. All right, so that is the use of the posterior distribution. So the posterior distribution tells us the probability of group membership based on these other things that you know about me. I'll just mention one thing. If I have a discrete distribution, so in my picture off to the right, I was assuming normal class-conditional distributions. If the class-conditional distributions are discrete, like a multinomial or binomial or something, then the class-conditional distributions can be written as what's the probability of x given y, whereas these posteriors are the probability of y given x. Well, where does the posterior distribution come from? The answer is it comes from Bayes' theorem. So we can write the posterior distribution as a function of the class-conditional distributions and the prior distributions. Now, if you don't remember Bayes' theorem, I have a separate video that you can watch at your leisure that covers Bayes' theorem for discrete random variables in the way that you probably saw it back in your first probability course. So if you don't remember Bayes' theorem, you can watch this video. You're going to see this is Bayes' theorem right here, and it looks a lot like this formula that I've given. So I've got a class-conditional distribution times a prior divided by the sum of all class-conditional distributions multiplied by their priors. In this case, the a sub i's are the priors. Here are your class-conditional distributions. And so, again, I have a prior times a class-conditional divided by the sum. All right, you can watch that on your own. Now, definition. The maximum likelihood discriminant rule simply says this. We're going to assign a training case with values x to the group y with the largest value of the class-conditional distribution. So all we're going to do is go find the values of these class-conditional distributions and go make the assignment. So let's go back to my picture here for a second. And we're going to consider applying the maximum likelihood rule to my three x's. So let's look at x1 again. For x1, this is the class-conditional value for the defaulting group. This is the class-conditional distribution for the non-defaulting group. We are going to call this one a defaulter. A defaulter because this value is greater than this value. When it comes to x2, we're going to call x2 a non-defaulter. Non-default. Why? Because this value is greater than this value. So the blue curve is higher than the red curve. And then of course with x3, this is also going to be a non-defaulter because the blue curve is way higher than the red curve here. So here's the red curve going off to infinity. So now we can come up with a boundary. So this is called the decision boundary. Where do these curves meet? Well, the two curves meet right here. And so my maximum likelihood rule is simply this. Anybody with an x less than this point where they cross is a defaulter. So we predict default. Any value out here, we predict no default. All right, so that's the maximum likelihood rule. Just take the one with the larger value, and you have your classification. Now, there's another rule that you'll see with a lot of different machine learning methods. So the other rule is called the Bayesian discriminant rule. The idea of a Bayesian discriminant rule is simply this. Assign an x to the group with the largest posterior probability. Equivalently, you can ignore the denominator here. So the denominator is just a constant. On my next page, that's the probability of b. Okay, but that denominator is just a constant, and therefore it's the same for all classes. So an equivalent way is just compute the numerator and assign it to the largest numerator, because if I divide that numerator by the same constant across all my groups, it doesn't change my my allocation, the group I assign that to. So let me go back to my example here, and let's continue on with x2. So remember, I wrote out some probabilities here. So the class conditional distribution, well, these are the probabilities. The whole idea is that if one of these groups is very rare, so let's say the non-defaulters are very rare. I hope that's not the case, but if that were the case, when I multiply this by the probability, and if that probability is small, I could actually end up classifying x2 as a defaulter. If my prior information is that most people default, then with Bayesian, I would call this person a defaulter, where with maximum likelihood, I would call that person a non-defaulter. So the Bayesian takes into consideration this prior information of how common the two classes are. All right, so that's the idea of a Bayesian discriminator. All right, well, let's now go ahead and solve this problem that I've laid out for us. So I gave us a concrete example where we had x as a single x, which is, so p equal to 1 is the credit score, and we have defaulters and non-defaulters. I'm going to make a further assumption that I have a common variance between these two groups. Therefore, I have two normal distributions that have the same dispersion. The only difference is they have a different mean. So why don't we go back and draw ourselves a fresh picture of this. And so this is what my picture is going to look like. I mean, it's basically the same picture I had before. So this is my y equal to 1 distribution. Call that mu1. And I'm going to try really hard to make this normal distribution have the same variance. This would be my y equal to 2 distribution having mean 2. And now I have a common variance. So the variance of both of these distributions is sigma squared. So this is called the equal variance case. All right. So I'm now going to develop the maximum likelihood discriminant rule using algebra. So what is the equation of these two curves? Well, you may have covered this back in your probability class. You may have skipped it, but I'm going to give you the equation of one of these curves. So the equation of one of these curves is this thing. So just a couple things to note about this. First, I have a subscript for the mean. So I have mu1 and mu2 in this case. Second thing you should notice is that your sigma squared does not have a subscript. So that's because the variance is common across the two groups. All right, so remember the maximum likelihood rule? The maximum likelihood rule is assigned to class 1 whenever the class-conditional distribution for group 1 exceeds the class-conditional distribution for group 2. So visually what that says is right here is the point of intersection. We're going to call these class 1. We're going to call all these people class 2. So those are our assignments. That is the maximum likelihood rule. So another equivalent way of writing this rule is I could divide both sides by F2, because then I have this ratio, F1 over F2, and if I have F2 over itself, I get 1 on the right-hand side. All right, let's go write in our two expressions. So I'm going to go drop in this equation for group 1. So that's just the class-conditional distribution for group 1. Here's my class-conditional distribution for group 2. And that looks like a very messy equation. There's a lot of stuff in there. But what I'd like you to notice is, first off, these terms cross out. So that term goes away. Then what we're left with is just the, I have an exponent divided by another exponent. It's going to be this exponent plus this exponent. So the plus comes from the fact that this is in the denominator, so that negative sign is going to become a plus sign. Anyway, I'm going to have to do a bunch of, a little bit of messy algebra if I do that messy algebra, I end up with this expression. I don't know if you, do you want to see that messy algebra? So I'm going to do the messy algebra. If you don't want to see it, you can fast forward on the video. So let's just go write that expression out. f1 at x over f2 at x is equal to 1 over the square root of 2 pi sigma squared. All of that is under the square root. 1 over the square root of 2 pi sigma squared. Then what we had was e to the negative 1/2. This was x minus mu over sigma, mu1 squared. This was e over 1/2 x minus mu2 over sigma squared. And that has to be, we're going to assign to class 1 whenever that's greater than 1. So those two terms cross out. And what we're left with here is e. I'm going to have negative 1/2 to the x minus mu over sigma, that's mu1 squared. Because this is in the denominator, it's going to be plus 1/2 x minus mu2 over sigma squared, and all that has to be greater than 1. Well, I can just take logs of both sides. So we're going to log both sides. Let's take the natural logarithm of this, take the natural logarithm of this, and what are we left with? Well, the log of e to the something is just, well, this is going to be minus 1/2 x minus mu1 over sigma squared plus 1/2 times x minus mu2 over sigma squared. What's the log of 1? That's the log of 1, which is 0. All right. Now I'm going to add this term to both sides. And I'm going to take this out of the denominator. So if I do that, I'm left with 1 over 2 sigma squared times x minus mu2 squared greater than, okay, I'm going to move this over to the other side. This becomes 1 over 2 sigma squared x minus mu1 squared. Now, notice these terms go away, and we have a fairly simple expression. So let me write out exactly what this is. So assign to class 1 when this is true. Well, what is this? What is x minus mu2? Note, x minus mu2 squared has a very important interpretation. This is the squared distance from x to mu2. That's just the squared distance from x to mu2. So if I had, for example, this is my x, this is the distance between x and mu2, and I can square it. If I had an x down here, if I took x minus mu2, that would be a negative number, but if I square it, it's the square distance. What's the thing on the right? Well, this is just the square distance of x to mu1. So what I'd like to point out is simply this. We're going to assign an observation to class 1 whenever that x is closer to mu1 than it is to mu2. So that's such an important result. I'm going to write it out. So assign to class 1 when x is closer to mu1 than to mu2. All right, so x minus mu1 is smaller than x minus mu2. So that's the distance, the square distance from x1, that's the square distance to x2. We're going to assign to class 1 whenever we're closer to x1. Now, having said that, this becomes extremely easy. This is just the average of the two. Mu1 plus mu2 over 2 is going to be that point. So all the points to the right of the mean of the means are closer to mu2. All the points to the left of that mean are closer to mu1. So it's extremely important to understand that intuition that we're going to assign to class 1 whenever x is closer to mu1 than mu2. All right. Now, I could go off and expand the sum of squares. So, this would be x squared minus 2x mu2 plus mu2 squared. And I simplify a little bit. What I'm going to get is something called a discriminant function. So a lot of software report these discriminant functions. R really doesn't. It's not a simple interpretable discriminant function the way you get from other software packages like SAS or SPSS or Minitab. But the point I want to make is we will often have this discriminant function that is just a linear function of x. So think of this as some constant plus some other constant times x. That's a linear function. So the point is, what you could do is just go compute your discriminant functions for each of the classes and assign x to the one with the largest discriminant function. So that's basically what I said right here. Assign x to the class y with the largest value of the discriminant function. Another thing that we can do is take that expression that I had. So this is the log of class 1 divided by class 2, which looks a lot like the logit function. This is just the probability in class 1, 1 minus the probability in class 1. So that is the logit function. And we can write out a closed form expression for the coefficients. I have some constant plus another constant times x. So it looks like logistic regression, but the parameters are estimated a little bit differently. So that's moderately important. All right, I think that's a good place to stop part 1 of classification theory.